Hi everyone, my name is Andrew Aziz, and I will be presenting the paper titled Large Design Models, Floor Plan Prediction in the Age of Generative Pre-trained Transformers. So the integration of machine learning with architecture has largely focused on the generation of floor plans to increase the efficiency of the design process in the early phases. Recent work in this space has focused on the use of generative adversarial networks, also known as GANs or image-to-image translation systems, to generate floor plans given a building footprint. This paper looks to large language models and the underlying transformer architecture for the purpose of generating architectural floor plans. Using a character-level token prediction model, this paper proposes an approach for floor plan generation given either a partial or no prompt of a sample floor plan. Using NanoGPT, which is an open source generative pre-trained transformer model, this paper trains the model on an ASCII converted dataset of house floor plans and predicts completion tokens before converting them back to spatial maps or floor plans. Qualitative evaluation of the results showcases both a clear spatial logic in the sequentially generated token completions while offering a highly efficient training time for floor plan generation techniques. So to provide an overview of this presentation, we will go through an introduction to the paper and its premise, review existing work in this area, detail the methodology for working with these large design models before discussing the outcomes. The production and development of floor plans is a fundamental aspect of the architectural design process. One of the many potential trajectories of machine learning and artificial intelligence in architecture is in the generation of floor plans as an iterative design tool whereby architect and computer can collectively design and work through floor plan options with much greater efficiency. Much of the existing work with respect to floor plan generation using machine learning has focused on generative adversarial networks, also known as GANs, including systems such as ArchiGAN, among others. While serving as a key milestone into artificially generated floor plans, this approach largely requires a predefined building footprint of a singular typology for it to infill with the appropriate spaces. The training of these GAN-based models are also very time and resource intensive, taking anywhere from 33 to 36 hours, depending on the graphics card used. In an attempt to explore a mode of floor plan generation which can offer greater control over the scale and layout of a generated design by being given a prompt, this paper looks to large language models such as ChatGPT, Llama, and BARD, and the closely related transformer architecture. Using a technique known as attention, generative pre-trained transformers, or GPT, decompose an input into chunks or tokens, learn patterns between the relations of said tokens at a variety of scales, and are then able to generate new tokens based on those patterns. This paper, as a result, asks the following question: how can large language models and next token prediction use the underlying transformer architecture to generate floor plans? A literature review was conducted to contextualize this approach of using the transformer architecture in large language models as a tool for floor plan generation. The review focused on the existing research around deep learning with respect to floor plan generation, such as GANs and pix-to-pix. To provide a context into the specific trajectory of this paper, other work into transformers and large language models also was reviewed. So, generative adversarial networks represent the primary existing approach for architectural floor plan generation using deep learning. GANs were proposed in the paper Generative Adversarial Nets by Ian Goodfellow et al. In 2014. They function by simultaneously training two models, a generator and a discriminator, which work in a reciprocal and adversarial process in order to adjust their parameters and improve their respective performance. A subsequent model introduced called Pix-to-Pix built on the generative adversarial nets paper and allowed for image-to-image translation, directly leading to the trajectory of generative floor plan research, such as ArchiGAN shown here. Pix-to-Pix introduced a way to guide GANs which proved fruitful for architectural floor plan generation, as a building footprint could be provided from which the layout could be generated. Here is another example of GANs being used to generate apartment floor plans given a footprint. This paper explores a novel trajectory for floor plan generation, which leverages the transformer architecture in a next token prediction model, taking advantage of the transformer's efficiency and accuracy. The transformer architecture introduced in the paper Attention is All You Need served as a key development in the emergence of large language models, or LLMs, and next token prediction. The transformer introduced an approach which consisted of a sequence transduction model based entirely on attention, replacing the recurrent layers most commonly used in encoder-decoder architectures with multi-headed self-attention. It is this transformer architecture which shows great potential for generative tasks such as floor plan generation. This paper seeks to leverage the transformer as a sequential next token predictor in order to perform, quote, design completion for floor plans in which it can generate tokens running left to right based on either no prompt or a provided partial prompt akin to an LLM. So getting into the methodology for this paper. So this paper utilized the Planify version 3 dataset, which consists of 1,042 unique housing floor plans extracted from real estate websites with individual colors identifying both the programmatic spaces and architectural elements, such as walls, doors, and windows. In total, 7 spaces and elements are plotted with the colors shown in the image. This color mapping is maintained throughout the paper. Of the total 1,042 floor plans, the first 1,000 were selected to be included in the dataset used for training, with the remainder serving as samples from which the partial prompts could be drawn from. These images were each plotted and converted to ASCII characters based on the color at a given resolution grid of 80 pixels or characters wide. Each color, representing a space or element, was also assigned a corresponding ASCII character. Each of the floor plans were combined in a .txt file, separated by a row of separator characters to denote the end of a given floor plan and the start of a new one. This image shows a sample of this training dataset after its conversion to ASCII characters. By converting the floor plan to ASCII characters, it allows for them to be processed as individual character level tokens, such that new tokens could be generated from the GPT model. The open source Nano GPT model was chosen for this paper due to its malleability with respect to training entirely custom datasets. It is a character level model that, when trained on open web text, is able to reproduce GPT-2 with 124 million parameters. It contains a train.py file, which performs the training, and a sample.py file, which generates the samples. For this paper, the GPT being trained is a 6-layer transformer with 6 heads per layer, 384 feature channels, using a block size of up to 128 characters or tokens. The model is trained on the TXT file of the ASCII converted floor plans. The total length of this dataset is 1,137,323 characters or tokens. Of this, 90% of the tokens are assigned to the train bin and 10% are assigned to the validation bin. Training the model on 1,000 floor plans from the Planify version 3 dataset takes 3 minutes and 13 seconds using one A100 GPU. The best validation loss for this training was 0.2876. So there were 3 token generation trajectories explored for this paper, each with a varying amount of context from a sample floor plan provided. No context, 1/3 height context, and 2/3 height context. The ASCII prompts and the respective images are shown in the slide. A further description of the context provided, as well as the parameters set for the design completion generation, are also shown in the slide. A larger number of tokens was requested from the generation which had no provided context to explore the transition from one generated floor plan to the other and to study a larger number of plans due to the unpredictability. The generations for all the different contexts provided an output of a stack of floor plans separated by a row of separator characters, which identify the termination of each individual floor plan. The generated ASCII characters were then mapped back to a space map or floor plans by converting each respective ASCII character to a pixel with a color equivalent to the original mapping outlined. So this paper studies 3 variations of design completion, or generating and predicting the next series of tokens which follow the prompt, to study the effectiveness of such an approach. As mentioned, these variations are the no context prompt provided, generating tokens without any guidance, 1/3 height of a sample floor plan being provided as a starting prompt, and a 2/3 height of a sample floor plan being provided as a starting prompt. In the initial iteration of the study, the trained NanoGPT model was asked to generate 10,000 tokens without any provided context prompt. A selection of the results generated by the model is shown in the image. The raw generated text outputs from the model as ASCII characters widely varied from being house-like spaces to merely a small scattering of ASCII characters. When these text outputs were converted to images, the results which appeared house-like were promising in terms of having spaces that were generally logically structured, with balconies being attached or adjacent to the outside walls, general space being centrally located, and bedrooms situated along the outside walls. There was also variation in terms of interior partitions, room sizes, and the number and type of spaces that were allocated. In the second iteration of the study, 1/3 height of a sample floor plan was provided as ASCII characters as a starting context prompt from which the model could continue to generate tokens. 2,000 tokens were requested per sample. A selection of results is shown in the image on the slide. Given the minimal initial direction the model was given, there was large variation in the outputs. The outputs showcase logical architectural spaces, identifying the need to circulate between secondary rooms, such as bedrooms and bathrooms, as well as assigning partitions accordingly. The building footprints also varied widely, yet accommodated the respective spaces in a structured and logical manner, such as creating niches for specific rooms, for example. While this option still only provided a small number of characters from which the model could use to predict the next tokens, the outcomes were much more predictable and structured than the previous iteration of the study, which did not have any context provided. This iteration shows that should a few key spaces be generally defined, even just identifying a small portion of these spaces, for example, the process identified in this paper of using a GPT model to generate tokens for the remainder of the building is promising. In the third iteration of the study, 2/3 height of a sample floor plan was provided as ASCII characters as a starting context prompt with 2,000 tokens requested per sample. A selection of results is shown in the image on the slide. With an increased amount of context provided, the generated outcomes are much more predictable when compared to the no context and one-third context prompts. This led to structured layouts, extending the existing rooms, and adding the respective partitions. Building footprints are also designed logically based on the spaces defined. There is also architectural logic to the placement of spaces, where bedrooms and balconies are located adjacent to the exterior boundaries of the generated footprint. This iteration showcases an opportunity for generating design options for a house that has already been partially designed, with at least one half of the house being generally resolved, for example. So this paper shows great potential for the use of a character level token prediction model to generate floor plans. For architectural use cases, providing a starting prompt, at least a few rows of a floor plan layout converted to ASCII characters, begins to offer some level of control over the design options generated. In conclusion, the character level token prediction is able to identify patterns in ASCII converted floor plans and generate sequential tokens which represent logical spatial arrangements and variations given either a partial or no prompt. Of key importance is the speed at which this approach works to train the model, taking only around 3 minutes. Other approaches which leverage GANs can take anywhere from 33 to 36 hours of training time depending on the graphics card and size of dataset. Given that the approach this paper proposes relies on a character level token training and prediction, increasing dataset size can continue to scale efficiently. This efficiency offers an opportunity to train sufficiently large datasets for large-scale programmatic types, such as malls, retail, airports, and other programs. Future work in this realm involves developing this approach of character-level token prediction in the context of a large language model, such that it can be controlled by a natural language input. Further tuning of the hyperparameters such as block size and expanding the dataset resolution beyond 80 pixels or characters wide offers an opportunity for generating a more detailed output. Additional future research related to this work involves using a varied dataset of multiple programmatic types to study the opportunities of using character-level prediction for many different typologies within the same model given a partial start prompt. Thank you very much.